Now, in the last lecture, we have derived the decay constant or rate of transition within the framework of the time-dependent perturbation theory, which is known as the Fermi's golden rule. Now, that expression, the lambda decay constant, involves two factors mainly. One is the matrix element of the perturbation with respect to the initial and final states. That is, the initial state is the unperturbed, say, parent nuclei, and the final state is the daughter nuclei and the electron and the antineutrino. And another factor which is involved, which we have to calculate, that is the density of energy states, D and D. Now, today we shall discuss the beta decay, theory of beta decay for the allowed transitions, which is known as the Fermi's theory of beta decay. Now, in the allowed beta transition, it is assumed that both the leptons, the electrons and the antineutrino, or the positron and the neutrino, they leave the nucleus with zero orbital angular momentum with respect to the nucleus. Now, therefore, in the allowed beta transition, both the leptons are emitted with zero orbital angular momentum with respect to the nucleus. Therefore, the transition rate lambda or the decay constant from an initial state I to final state F that is given by the lambda is equal to 2 pi by h cross this h prime if matrix element mod square and dn de 0. So this is your equation number 1. This is the density, this is the matrix element which you have to calculate over the initial and final state, over the perturbation, and this is the number density of states. For this, we know that HIF prime, that is equal to the matrix element psi F star H prime psi I vector. Is the matrix element over the initial and the final state. Now, for simplicity of calculation, here it is assumed that this perturbation H prime, that is a constant quantity. Okay. So H prime is a constant quantity for simplicity of calculation, and the initial state is the wave function of the beta unstable nuclei, parent nuclei, And final state is the product of the wave function of the daughter nuclei, an electron and an antineutrino, or in case of say positron emission, the daughter nuclei, positron wave function and the neutrino wave function. Because the final state, there are three particles, the daughter nuclei, the electron and the antineutrino. So the wave function will be the product of these three. So the final wave function is the product of these three quantities, wave functions. So the initial wave function is the wave function of the parent nuclei, which is beta unstable. Now for simplicity of calculation, the interaction Hamiltonian H prime is taken to be a constant. Suppose it is G. The initial wave function is the normalized wave function. Of the unstable parent nuclei say psi in, and the final wave function is the product of the daughter nucleus the electron and the antineutrino. So this is the initial wave function, and psi fm, the final wave function, is the product of these three. Now, therefore, the equation 2 becomes that is the H prime matrix element IF. H prime is taken as a constant G, so it can be taken out of the integration. Then you get psi Fn star daughter nuclear wave function, psi E electron wave function, psi nu bar antineutrino wave function, and the initial wave function psi In of the unstable parent nuclei. So this is the matrix element we have to calculate. Equation number 3. Now here we assume that this lepton wave function, the electron and antineutrino wave functions, they are replaced by some their constant values at the nucleus, because the energy involved in this interaction is very small, weak interaction. So the electron and lepton wave function, they have the very small energy. If energy is very small, so momentum will also be small. So if momentum is small, then according to de Broglie's hypothesis, the wavelength associated with these particles, they will be quite large. They are much larger compared to the nuclear dimension. So they are replaced by the plane wave, and their maximum value is the unity, is a constant value is there. So we consider that the wave function of electron and antineutron is a constant quantity within the nucleus, because their energy involved in this process is very small. So they are replaced by a constant normalized wave function. Now the lepton wave functions are replaced by their constant value at the nuclear center. Since the wavelengths of the leptons are much larger than the nuclear dimension. So the electron and the antineutron wave functions will be expressed by constant value, normalized wave function. Now, if we consider that the plane wave, now if the system is enclosed in a volume V, then the normalized wave functions are, we consider the electron and the lepton are free particle wave, because the energy is very small, so we consider it is as a free. So they are represented by a plane wave. So their wave functions are written as psi E r. It is g to the power minus half e to the power I k e dot r. E to the power I k dot r represents the plane wave, and psi nu bar r, that is v to the power minus half e to the power I k nu bar dot r. These are the wave functions. Plane wave function represented by the free particle wave function. Now, this is equation number 4. Because the energy involved in this process is very small, so they are treated as a free particle. Now, how the normalized wave function is v to the power minus r? The normalization constant n, as it is well known to all of you, that how to find the normalized wave function, that psi suppose say psi E star electron expansion we consider psi E d tau, that is equal to unity. So if the wave function is n e to the power I k e dot r, then we get n square e to the power I minus I k e dot r into e to the power I k e dot r d term, that is equal to unity. So this is the integration over the whole space. This is the 1, so you get n square into v. This is the volume over which the particles are enclosed. That is equal to 1. So you get n equal to v to the power minus r. Okay, so normalization constant v to the power minus r and plane with it. Now, if we substitute all these values in the expression for a fixed element h time, then what we get? Now then, but before going to this, we know that the antineutrino is a neutral particle. So the other charge of the other nucleus or the charge of the atomic electrons will not affect its wave function, but the electron is a charged particle. So this wave function will be affected by the other nuclear charges and the presence of the atomic electron. So there is a Coulomb distortion will be there. So for electron wave function we have to multiply it, or we have to add a Coulomb factor in the expression. Now the electron wave function is distorted by other nuclear charges or by the atomic electrons. Therefore, the wave function the psi E mod square, only the electron wave function, should be multiplied by Coulomb factor. This is called the Coulomb distortion, which is written as F. This is Coulomb factor Z E, energy of the electron, that is twice pi eta. Eta is the Sommerfeld parameter, comes in terms of the atomic number, e to the power minus twice pi eta. Where eta is the called the Sommerfeld parameter, comes in terms of the atomic number, that is the charge present in the system. Now, where this factor is eta, where this factor eta is equal to plus minus z square by 4 pi epsilon 0 h cross v, 4 pi epsilon 0 h cross v. Now this plus sign is for electron. The plus sign is for electron and the minus sign for positron. So we have to finally multiply this Fe Coulomb factor in the decay constant expression lambda. Now therefore, if we substitute all these values in the now from equation 3 and 4, from equations 3 and 4, what we get? We get that the matrix element H prime I over the initial and the final state, that is the perturbation Hamiltonian, which is here taken as a constant quantity, d to the power minus 1, which comes from the electron normalized wave functions, psi Fn star wave function of the daughter nuclei, psi In wave function of the parent nuclei, and d term. So H prime I mod square, what we get? We get d square by d square, and this is the matrix element over the daughter and the parent nuclei, which we write as MIF mod square, where this MIF is equal to this one, this psi star Fn psi In d. This is equation number 6. So we have to calculate this because this quantity is involved in the decay constant. Now we have to calculate this. This matrix element can be calculated if the nuclear structure of the initial and perturbed nuclei structure and the final daughter nuclear structure, if this nuclear structure are known to us, then this MIF can be calculated easily. So finally here we have not included the Coulomb factor due to distortion of the electron wave function by the presence of the other charges. So finally, if we multiply this by the Coulomb factor, then this now considering the Coulomb effect, here we have not considered the Coulomb effect. The HIF mod square, that will be equal to your d square by d square F Z E into this MIF mod square. This is your final expression for the matrix element over the initial and the final state by considering the Coulomb distortion of the electron wave function. Now, so this thing is calculated by this one. That means you have to calculate this one if the nuclear structure of the parent and the daughter nuclei are known. Now the second thing one is involved, that is the number density of the states, final states, where the system goes after transition. So number density of energy states we have to calculate. That is dN dE0, which is involved in the decay constant lambda. Now to calculate this dN dE0, another factor to calculate this number density of states, final states, dN dE0. It is assumed that the system is enclosed in a impenetrable cubical box of length L, capital L. That is, we have a impenetrable cube of side L with origin at one corner. Now, the weight function of a particle in a cubical box that is given by psi equal to A sin kxx sin kyy and sin kz z. Because it is a three-dimensional box, you are very much aware of the wave function in a one-dimensional box of length L, that is A sin kxx. Now it is a three-dimensional problem, so in three dimension this is the wave function. Okay. Now if we apply the boundary condition, because the system is enclosed in a cubical box, so the particle cannot go outside the box. So at L equal to 0 and at L equal to L, the wave function must be 0. So by applying that boundary condition, one can find the value of kx. So at x is equal to y is equal to z equal to L, if we apply the boundary condition here, then we get this kx value is equal to nx pi by L. Similarly, ky equal to ny pi by L. Here nx is equal to all integral values 1, 2, 3, etc. Now therefore the total momentum of the particle that is p square, that is kx square plus ky square plus kz square h cross square. You got p equal to h cross k, so p square equal to h cross square k square. K is this one. Three components are here. So if we substitute the value of this k here, therefore you get the pi square h cross square by L square nx square plus ny square plus nz square. So this is your equation number 9. the maximum momentum of the particle. So each value of n, nx, ny and nz represents the state of the particle. Suppose nx is equal to 1, ny, nz is equal to 2 or n is equal to 3, then it is a state. Nx is equal to 1, this is 2, this is another state. So different values of n represents the different states of the particle. So the maximum length of this the maximum length of the vector, the maximum length of the vector n is n max, that is equal to p h cross pl by pi h cross, because n is equal to here it is n square, that is equal to p square l square pi square h square. So n max is equal to pl by pi h cross. Now if we consider a sphere with the maximum radius n max, to calculate the number density of states, we consider a sphere of radius n max. Now therefore the total number of states, because each value of this n, nx, ny, nz gives a different state. So how many number of states are there within that cubical box of length L? So to calculate that, we calculate the total number of states within the electron states within the volume V is equal to the 1/8 of the volume of a sphere of say radius n max. Therefore we have this number of states n within a cubical box of length s L is 1/8 and the volume of the sphere 4/3 pi n max cube, 4/3 pi r cube. Now substitute the value of n max. N max is this one, so you get v p cube by 6 pi square h cube. This is 1/6 pi and you get p square L cube, and then and L cube is the volume V. Here it is written. Now why we have considered in this way? Say 1/8 is the volume of a sphere. You have a sphere, so you get two hemispheres if you cut along the diameter in the horizontal plane. Now each hemisphere is cut by two perpendicular planes. So you get 4 parts. So in the lower part also you get 4 parts. So total you get 8 parts. So that's why, and each part is considered as a cubical box. So it is the 1/8 of the volume of the sphere whose radius is n max. Okay. Now therefore, the number of states in the momentum interval, the number of states, electron states, either electron or antineutrino, in the momentum interval dp, small momentum, that is p2p plus dp, we consider in this interval. So the interval is dp, that is obtained as dn v square, that is you have to differentiate it, 2 pi square h cube into dp. Just dn, this is 3 p square dp, 3 will cancel with this, that 2 will come here. Question number here. So in this small momentum interval, this is the number of allowed energy states for the electrons. Either electron or antineutrino can go in any one of these states. These are the allowed energy states. So the partial probability for decay, for decay into the momentum interval PE and P plus dP. In this momentum interval, what will be the probability of decay? That is probability P of P dP, that is equal to d lambda P dP this is the probability of decay in the momentum interval dP. Now, to calculate this, we consider here that fix the final state of the electron, because there are 2 electrons, one is electron and another is antineutrino. Both will go to the final state. Now to calculate the probability, we first consider that fixing the electron, that the electron is going to the state K, suppose the K state. That is the electron, we know for certainty the electron will go to that state. Now what will be the probability of this antineutrino to go any one of the final states? Because there are 2 electrons, so we have to fix one. So we fix the electron first, that it is going to the final state K. Now where the antineutrino go? What is the probability of antineutrino to go any one of the allowed energy states? Therefore we initially fix one. The electron is going to a certain state. Now let us suppose that the electron is going to the kth state, final state. Here it is assumed that the electron is going in the final state K. Now electron is fixed, then this dn be0 is the density of the neutrino states. Because the variable is anti-neutrino states. Now therefore the total disintegration energy this E0, that is the energy of the electron and the antineutrino. This amount of energy will be released by these two electrons, and dE0 is equal to dE mu, because here it is constant. We have assumed that the electron is going to the K states. So it is a constant quantity here now, not the variable. Now from the relation, relativistic energy relation, from the relation that E u bar square is equal to P square P u bar square P square C square plus rest mass M u bar square C square n to the power 4. C square is equal to P square C square plus M u square C to the power 4. This is the rest mass of the antineutrino. Now we use this relation, because the electrons are emitted with a high speed, so relativistic formula we have to use. Then we get dP nu bar is equal to E, from this relation E is equal to this, you get E nu bar divided by P nu bar C square d E nu bar P, and then differentiate it. So here E is a constant quantity, so you get E nu bar by P nu C square, and d E nu bar we have calculated, that is d E0, because electron distribution constant is energy is equal to E0 equal to E nu bar plus E is a constant quantity, so that is d E0. Now if we use the equation, we refer to the equation number 12, 48, 15 and 16 from equations 12, 14, 15 and 16. We use all these, combine these equations together, then we get d n nu bar, energy density of the neutrino states, that we get V by twice pi square h cube E nu bar square by c square minus m nu bar square c to the power 4 to the power half E nu bar by c square d e 0 and then dn nu bar de0 we take de0 here then you get v divided by twice pi square h cube 2 pi square h cross cube c cube e0 minus e 0 minus e whole square. In place of this e nu we have written it in terms of this minus m nu bar square c to the power 4 or to the power half. Equation number 17. If you substitute all these values from equation 12, 14 and all these things, then you get this equation. And in this equation, this E nu bar is replaced by E0 minus E. Therefore, now we have obtained this one, the number density of states. Now, if we substitute it in the expression for the decay constant, because our aim is to find lambda, the decay constant for allowed transition, then the decay constant lambda k. Why we are giving this k? Because we assume that the electron is going to the state k. That's why it is represented by lambda k. When electron state, final state is fixed. Now that will finally come. If you substitute all these values, you get G M I F mod square by pi V h to the power h cross to the power 4 c to the power c cube. The Coulomb factor F Z E E minus E0 E0 minus E and this factor E0 minus E whole square minus m nu bar square c to the power 4 or to the power half. Now the partial probability for decay into one of the electron state in the momentum interval dPe, that is given by probability PE which I have written earlier this equation, that is lambda K B N E. Now therefore we finally get, it is partial probability for electron, because we have initially fixed the electron is going to a particular state K. Now the probability of going the electron into any of the final states, partial, what is the partial? Not we are now fixing at the particular state K. Any of the states, that is P dP, that is equal to G square M IF mod square by 2 pi cube C cube H cross to the power 7 P square F Coulomb factor Z E0 minus into this factor E0 minus E whole square minus M nu bar square C to the power 4 whole to the power half. So this is the partial probability or the momentum distribution of the electron in the after decay, momentum distribution, by assuming that the perturbation is a constant quantity. Now if we substitute the neutrino rest mass is 0, neutrino rest mass is very very small. Now if we consider the neutrino rest mass is 0, then this equation becomes for M nu bar equal to 0, neutrino rest mass is 0, then this equation partial probability of the decay of the electron into any one of the final states, that is G square M IF mod square 2 pi cube C cube H cross to the power 7, you get P square is F Z E, and here it is 0, so you get this is square the power half, therefore you get E0 minus E whole square. One is from here, another is here. Now if you take these two factors here, on this side here, therefore you get P by P square F ZE that is you get this factor G square, that is MIF matrix element square 2 pi cube C cube H cross to the power 7 and E minus E0 minus E whole square. So if the square is not there, if we use this one, so you get G MF versus square root of this. If we remove this square, then in this side we get square root of this. And here also similarly, this it will be G, this is a m, this will be g, this will be m, and this is square root of this. So it is a constant quantity. Matrix element of this, if we know the nuclear structure of the initial and the final daughter and nuclear nuclei, it can be calculated. It is a constant quantity, all are constant. So if we plot the graph between this probability distribution with the energy of the electron, then you get y is equal to mx. So when this E equal to E0, that is the end point energy. This is the disintegration energy, that is the energy difference between the daughter and the parent nuclei. And where this energy, electron energy will be same with that one, that means neutrino is emitting with the very small energy, it is 0. Then in that case E will be equal to E0. Then this curve, this straight line cuts the energy axis at a value E0, that is the end point energy. And from the experiment, from this formula actually, if this calculated theoretical value will match the experimental value and consistent with the experimental value, then it is said that this Fermi's theory of this beta decay, allowed transition, are correct. And it is observed that the theory, Fermi's theory, is well consistent with the experimental value, because from the hydrogen 3, when the beta decay is taking place, the beta decay maximum energy is 18 keV, and in that case this straight line graph, when cuts the energy axis at 18 keV, that suggests that the mass of the neutrino is not 0 but 250 electron volt in energy unit. That is very, very small compared to the electron also. So in the next class we will discuss the experimental verification of this one, that what should be the maximum limit of this mass of the antineutrino, which is 250 electron volt.